So I guess a bit of a smaller class today. People are traveling. But okay, as always, we'll start with some logistics. So the project checkpoint thing was supposed to be due today. Pushing it until Saturday gives you a couple more days. Information about expectations are on that document that is on the class website. If you have any other questions regarding it, just post on Ed. And again, if you want to meet with me or our TA just to talk about it through vocals instead of through writing, we can totally do that. Just email us. Next week is the week of Thanksgiving. No class that week. And then the final week of classes, or the last class, is on December 5th. So that's the week after next week. So there you'll be doing some project presentations. There's also some information about that on the document. It's going to be quite short. It can be 5 to 10 minutes. If you want to go a little bit longer, that's fine too. You can think about this as a time to demo the work that you've done, maybe talk about the motivation for the work, some of your favorite accomplishments or things that you wanted to pursue further. I'm not setting too many boundaries of what you should and shouldn't talk about. I'll let you have the liberty in deciding what's applicable to talk about. But yeah, just be prepared for that, 5 to 10 minutes. And then the remainder of the class, we might have an extra anywhere from 30 to 60 minutes. We'll do a little bit of lecture stuff. I'm not quite sure what we'll talk about yet. That's partially what the poll on Ed was for that I just asked you to do. I'm still trying to decide something that would be interesting to the most amount of people. I already have one lecture that's fully planned, so in case nothing comes up, I'll just use that. But it should be pretty chill. So that's all there is to expect going forward. Any questions about schedules or the final project? Anything like that? All right. So, last week we spent some time talking about TSP. Remember, that was the question where you have this complete weighted graph and you want to visit all of the vertices in the minimum amount of weight or minimum amount of distance. And we talked a lot about different heuristics, which were called construction heuristics. We saw nearest neighbor, nearest insertion, furthest insertion, and savings. And all of these heuristics kind of started out with nothing. You just started at some vertex, and then you build up your solution. You can think about nearest neighbors, the greedy-esque one, where you just choose the one that's closest to you and add that to your path. You're building up your tour. Today we're going to look at something called improvement heuristics, where we're going to have a starting point that is going to be a solution to our problem. It might not be the best solution or the most optimal solution, but it'll give us a starting point. And from there, we'll try to modify it to improve our solution and hopefully get to something that ends up being really, really good. And so the main technique that we'll talk about today is called local search, which is the main idea behind these improvement heuristics. So this is what local search is. The idea is that out of all possible solutions to your problem, we're going to create a graph, something called a neighborhood graph. And so our vertices of this graph are going to be different solutions to the problem. So these are massive vertices, but let's just say that this vertex represents a solution to our problem. So it is taking perhaps a tour, V1, V2, V3, V1. So that entire tour, we're just going to say, let it be a vertex. And, we'll have a bunch of other vertices too, representing other tours. Maybe this is V2, V1, I don't know, V4. Maybe I should have had V4 here. And then V3, V2, something like that perhaps. And so a whole bunch of these vertices. And then edges are going to exist between our vertices if we deem the solutions to be similar to one another. And the word similar is kind of used without definition right now, but we'll define it more clearly in a moment. In simple terms, we'll say that if we can take one solution, maybe this vertex, which represents this solution, and do a very small, minor edit, where we will define what an edit is, and if that one single edit can produce solution 2, then we'll say that they're connected by an edge. So we'll just say vertices are connected by edges if they're pretty similar to one another. And we'll clarify what that means in just a moment. Howdy.
Sorry, you guys are good to go. Sorry, I just think we have the room from like now until 8:30.
Oh, there's a classroom now until 8:30 in here.
Wait, is that booked on the calendar?
Well, I mean, it's like an engineering class, so I don't know if it would be on the calendar. We had this issue before.
Yeah, usually like just in class, engineering classes are booked here.
Is there any chance you might be able to use a different room, maybe?
I can look. Yeah.
There's all of these rooms here are usually available, right?
That's true.
They're completely empty.
Okay.
We would really appreciate it. Thank you.
Yeah.
Appreciate it. Now, I know you guys have all decided on your projects, but a really good project would have been fixing this stupid scheduling system that Penn has. Anyways, kind of makes sense, our graph formulation. Each vertex is a solution. They're connected by an edge if they're kind of similar to one another. Good? Okay, so what we're going to do is like create this graph, start at some solution, and then continuously visit its neighbors. Hey, we'll continuously visit its neighbors until we get to a solution that is very, very good for our purposes. So to briefly recap for you folks, we're exploring something called improvement heuristics. So last week we were talking about iterative heuristics, building up solutions to TSP. Today we're going to start with some solution and then edit it until we get to a spot that we like. So, if we're dealing with a very, very big graph, if we think about TSP, the amount of solutions, the amount of vertices is n factorial, and who knows how many edges there are. And our idea is to just explore this graph. It's going to take a really long time. We can just keep on walking for a really long time. We have n factorial vertices to visit. So in practice, we sometimes like to incorporate some stopping time. So maybe we give up if we're searching for way too long. Like too many minutes have passed by and we just want to stop now. Otherwise it'll keep on exploring. Or maybe we have taken a large amount of steps. We have traveled along the graph 1,000 or 1,000,000 times. We'll just stop there. Or maybe as we're taking these steps and we're improving our solution, maybe we're just not improving enough. We're making very, very small progress. And if that improvement is too small for our satisfaction, maybe we'll just stop there. So these are things that you can include when you're building these algorithms in practice to make things a little bit quicker. So, I've kind of already drawn this out, but this meta idea of local search is very natural for TSP. Start with some tour, and then visit very similar tours as we're improving on our cost, and eventually stop when our solution is good enough for our purposes. So that's the idea. The main thing we have to define still is how are solutions connected to one another by an edge. Thus far I've been just saying if they're similar to one another, or if you can make a very small edit from one and you can reach another. So we'll define that properly now, and then that would give us the full graph visualization. Any ideas on maybe the answer to this question? What is a simple operation to transform one tour into another tour? It's not a super simple question actually, but just any ideas are interesting to hear. It's in some other room, sorry. Well, for me, like, I would think that if our tors are essentially permutations of vertices, and I have maybe this tor right here, and a second tor, these two are pretty similar to one another. The only thing that's really changed is V3 and V4 have swapped places, but everything else is pretty much the same. So perhaps our edit would be to maybe just change a very small amount of intermediary vertices in our graph. Like, these two are similar, but this compared to V1, V3, V2, V4, V1, these two are a lot more different from one another. So one idea is to use something called two adjacency and two optimality. So we'll say that two tors are called two adjacent if we can take one tor, delete two of its edges, add in two different edges, and we get T prime. That's going to be our edit operation. And I know right now it's in terms of edges, which makes it kind of confusing, but we'll see a visual in just a moment. So that's what two adjacent means. And we'll say a tor is two optimal if we can't make any more of these two edge insertion deletion edits and improve our tor. So as a visual, maybe we start on the left-hand side. That is part of our tor. We go from A to C to B to D. Then an example of a tor that's two adjacent to it is A, B, C, D. And so what we've done is we have deleted the edge A to C, we have deleted the edge B to D, and instead we have added the edge A to B and added the edge C to D. All other edges have either stayed or reversed directions.
Oh, how are we just allowed to reverse them?
Remember, we're dealing with a complete graph that's bidirectional. So if I can travel from C to B, then I'm also allowed to travel from B.
And we're
to
still operating
C.
under the same cost assumption, like that
Yeah,
C to B.
yeah, we'll just say equal cost. Yeah. So remove two edges, add in two other edges. The remaining edges either stay or reverse direction. And we'll say that these two tors are two adjacent to one another. And so to formalize the operation, we'll call it swap, where we have a tor as one parameter and two indices. And the formalization of this procedure is for the first I minus 1 vertices, everything that comes before I, we'll keep that part of the tor. Everything in between I and j inclusive, we'll reverse it. And then everything after j will stay the same. So in the example here, A, C, B, D, we're calling swap on that, index 2 and index 3. Perform that operation, and we get the right-hand side. So any questions on two adjacency or, I don't know, the swap operation? Okay, so then the heuristic is pretty natural. Start with a tor and keep on going until the cost of our tor does not decrease. We'll go through every pair of indices on our tor. We'll check the cost after we do that swap operation. If that's less than our current tor cost, then we'll just change the tor that we're looking at. So it's the exact idea of traversing this graph here. We start at one place, we check its neighbor. If that tor obtained by swapping is of cheaper cost, then we'll move to this vertex entirely. And we keep on going until we can't improve any further. Seems pretty natural. It's important to note that this heuristic still does not guarantee you will find the optimal solution. A natural question is, why? There is not a great answer that's very simple. The short answer is that you might get stuck in some local minima and you can't escape those. That's not a good answer. but maybe we'll see an answer in a few slides. We'll see if I feel up for it. But this does not guarantee you'll find the optimal solution, even though it feels like it should, that you start at a vertex and you keep on crawling to things close by to it and improving upon it. It should feel like you get to the optimal solution, but it does not guarantee it. So, of course, let's see it in action. So the starting point for this heuristic is a TOR. This is drastically different from last week's heuristics, where we started from just a vertex. We're starting with some TOR, in this case, ADCB. And then we would check. We'll go through every every pair of indices from 1 through 4, and we'll consider what happens if we do the swap operation. So for example, what happens if we call swap on our TOR with index 1 and index 2? And that swap operation said everything that comes before I should stay the same. So in this case, nothing comes before A, so nothing happens. Then everything in between 1 and 2 inclusive, A and D, should reverse. And then everything after 2, everything after D, should stay the same. So we've reversed A and D, and then CB remain. So that's the swap operation on 1 and 2. And we see that if we do that, the cost of that TOR is now 90, which is better than 95. So that would become our new TOR. We're now considering an entirely different new TOR. We have gone from one vertex to another because this one has better cost. And again, we would go through the pair of vertices, or the pair of indices. In this case, 1, 2. If you try to do the swap operation on that, you'll get this TOR, which is the same as before. That's 95. It's not better, so we don't change anything. Then we check the next pair, 1 and 3. Call the swap operation. See what the cost of that is. In this case, it's 90. We're not improving, so we don't do anything. And we keep on going until we find something that improves it. In this case, 1 and 4 does not improve it. But if you do swap on 2, 3, which means everything before 2, you keep the same. Everything in between 2 and 3, A and C, swaps. So C and A. And everything after 3, B, stays the same. Now we've improved. So we're now seeing another vertex that is of cheaper cost. So we would move to there. And so on and so forth until you can't improve any further. And in this case, I think this is probably optimal. Yes?
Does this become really bad if you are not allowed to reverse the edges freely? Or is this still useful?
Can you repeat that? I don't think I understand.
Does this become really bad if you don't have the same cost on both of your bidirectional edges, so you can't reverse the edges freely? Or is this still useful?
I'm not too sure about that question. My guess is that it would not work perhaps as well, because right now we're just taking for granted that everything that's doing reversal, it stays the same, so the cost remains the same. But I mean, I guess you would have to do another, you would still do these checks for cost, you do the swap operation, you can check the cost, and I suppose if it is improving, you can still go. So nothing really changes in terms of the construction, it's just something that we took.
It doesn't add any runtime. You're just checking all of them.
No, because you're still checking the.
Yeah.
Good question. Okay, questions on 2-opt? Yeah.
Why 2? Why not 3?
Why not 3? So, yeah, it can easily generalize to 3-opt, 4-opt, and k-opt. The reason I chose 2 is because it's a good starting point, and it's a lot easier to draw with the visual of deleting 2 edges and inserting 2 edges.
Technically, n-opt by definition gives you the most optimal answer, right?
I suppose, yeah, but very expensive operation. So yeah, it's very easy to generalize. And in fact, there's this Lynn Kernighan, let's just say that, heuristic, which takes the idea of 2-opt, as well as a bunch of other of these opts, and dynamically changes k over time based on several criteria. I don't really know the details of this. You can research it if you want to. But this ends up being one of the most effective TSP heuristics. So pretty interesting fact there. Cool. Okay, then let's take a step away from TSP. Not yet. Same graph from last time. Now we'll see where 2-opt, 3-opt, and LK appear, which is way down here. So in comparison to everything we saw before, the solution of these tends to be better than those constructive heuristics we saw last week. Runtime is comparable, so that's fitting into the picture. And I figured maybe people would ask this repetitively. Let's see what happens if I click on this. So this is a question asked 7 years ago, that why doesn't 2-opt return an optimal solution? And blah, blah, blah. There's a bunch of responses there. No one responded to this question except for the dude himself or herself. And this is a visual that if you can convince yourself as to why this may happen, that'll tell you that the answer is like, yes, it doesn't always get you optimal. And the idea is that while doing this graph search, you might end up in this solution right here, whereas the global solution, or the global correct minimum, is this. Distance in this case, like the edges have a weight equivalent to their distance. So like it would literally be like 4 centimeters here, so this would have weight 4. So this one happens to be a local optimum, which means you can't perform the swap operation on this graph and improve its overall weight. However, the best solution amongst these vertices is that right there. So that's just one example. Yeah.
Is there a heuristic that goes like, oh, if you hit a local, like if you are doing 2-opt and then you realize that there's no more 2 edges that you can change to make it better, at that moment you switch to like 3-opt or 4-opt or something and then keep it.
That's what we saw.
So I think Lynn Kerningham might do that. But there are other very similar things that you can do, and we'll talk about that in just a moment. But yeah, okay, that should hopefully convince you that no, it's not always optimal. Okay. We'll take a step away from TSP and revisit SAT. So we can use local search for SAT. It's not an optimization problem. TSP was. We had an idea of what makes it better. A cheaper cost Tor is better. But we can still actually try to use local search for SAT. So a solution will be any truth assignment, even if it isn't satisfying. So now these vertices are going to, again, they're still going to represent solutions, but now it'll be x1 equals true, x2 equals true, x3 equals false, so on and so forth. Again, this idea of vertices representing solutions, same thing, just different looking solutions. And again, we have to define our neighbor relation. What connects two vertices? And remember, we're looking for something that says our solutions are very similar to one another. With TSP, it was, we can just do this simple edge operation that's very small. And if we get somewhere else, then they're connected by an edge. So in the world of SAT, what could be a good neighbor relation? When would we say that two solutions, two variable assignments, are very similar to one another? Keep it as simple as possible. Take a look at the ones I gave up here. Would we say that these two are similar to one another? True, true, false, and true, true, true?
Yeah, it's one inversion away.
One inversion away? Yeah, like if they differ by one, if one variable assignment is different, then they're probably pretty similar to one another. So maybe we'll use that. So the idea is that the edge will exist if they're one variable away from one another, and the operation, similar to the swap operation that we did, is now going to be just flipping a single variable. I can get from this vertex to this vertex by flipping x3. they share an edge because they're one variable definition away from one another. So edge is one variable away, similar to the kind of closed solutions. Operation, similar to swap, is flipping the vertex. Questions on this thus far? Okay. What variable do we flip? So, it's not a great question, but the idea from before is that, like, with TSP, we had this idea of overall cost, that we could check all of the swap operations and choose the one that improves our cost. Here, there's nothing really telling us that, like, oh, your SAT solution has really good cost. We need to build up an idea of, like, what it means to have a very good SAT solution. So how would we choose which variable we should flip towards getting to a solution for our SAT? So in other words, maybe we have a solution here, and this is the satisfying assignment. Right? We'll just say our formula is satisfiable. This vertex represents the assignments that will satisfy the assignment, satisfy the formula. And of course, we have some starting point and a whole bunch of edges.
Yes.
How do we now know which neighbor to visit that would get us closer to SAT, the colored in vertex? I'll give everyone a minute to think about this because it's important for understanding the idea as a whole. Any ideas? Yeah.
Well, this might be stupid, but like, isn't this just a traveling salesman problem and you need the shortest cost route to get to your destination? So like, if every edge is like the same weight, that's even shortest path actually, I don't know.
Yeah, I mean, that's an idea, right? We're trying to, I guess we're like maybe trying to find the shortest path. But again, it's a huge graph too.
But won't the shortest path always be the fastest way to like get there if you're only allowed to switch one variable at a time? Because all of the edges mean that you're having one inversion. So the least number of edges, that should be the best way to get to the optimal solution, shouldn't it? Like, you just call BFS because it's like undirected equal weights, and then I don't know.
Maybe I didn't think about that. Let's see. I'll think about it. Maybe. I think there's something I'm missing.
Do you know ahead of time what the endpoint is? No, okay.
No. There you go. That's the solution then. Yeah. Because, but I guess like as you're conducting BFS, then you take the vertex and then check that to see if it satisfies.
Yeah.
Because
You can
BFS
keep
doesn't need an
dynamically
endpoint.
checking.
I don't know.
Is there any here that we're expanding it, or that we just follow one path until we reach SAT?
Could you summarize the problem again?
Yeah, so with TSP, we had our vertex to start from,
Yeah.
and we would, I guess, check all of its neighbors, or like one by one check its neighbor, until we found a vertex that improved our solution.
Yeah.
And we kept on doing that continuously. We'll do that similar idea of starting at a vertex, moving to vertices that improve our solution, and eventually stop when we can't improve it any further. So the question is, how do we know what it means to improve our solution? How do we, without knowing our satisfying assignment, how do we know that we're on the right track?
Yeah, I still can't convince myself why just BFS doesn't work.
I think
Yeah.
so, but because you have to check every neighbor. But the idea of the greedy algorithm is that you don't. You just take the best closest odds.
Right. So like, I think the answer that I had in my head is that if we're doing BFS on a graph that's exponential size, because there's 2 to the n vertices, it's going to take like upwards of exponential time to find that vertex. If we attempt to be greedy, as we have been with TSP, then we're not necessarily falling into that exponential time thing. We're just going, one by one. And maybe worst case, we get to something exponential, but here's just one simple improvement. So maybe the idea is that we'll flip a variable that makes the most amount of unsatisfied clauses become satisfied. So, all of these don't yet satisfy our formula. Maybe this one, maybe there's 100 clauses to be satisfied, and maybe this solution satisfies 20 of them. So maybe we'll go to the neighbor that makes the most amount of unsatisfied clauses. So out of the other 80 ones here, whichever one makes the most of those satisfied, we'll move to that neighbor. Thomas?
So in this case, we have some particular vertex that corresponds to a satisfying assignment.
Yes.
But then what's the point?
Because we're trying to find not a satisfying assignment, just an assignment of truth values to our variables. And we're trying to find the assignment of truth values to our variables that does satisfy the formula. There's still this formula phi that exists with your clauses and stuff. So we're trying to find this assignment that satisfies phi. All of our vertices are just assignments of variables to truth or false.
So we start with some assignment, then we traverse the graph until we find some vertex.
Bingo.
So then, how do you determine what vertex to start? Do you just randomly?
Yeah. The idea with these improvement heuristics is just start from any solution and then incrementally try to improve that until we hopefully get down there. So back to this idea. Maybe this one has 20 satisfied and 80 unsatisfied. We'll call it US. And of these 80, maybe this solution satisfies 60 of these. And that's the most out of all of its neighbors. Maybe the other neighbor satisfies like 15 of these and 30 of these, so on and so forth. Seems like a good idea?
Can it cause the already satisfied ones to become unsatisfied?
Yes.
So just you add that too.
Yeah. So the main issue is exactly what Chris mentioned. That, just by focusing on the unsatisfied ones, satisfying that is great, but we are changing a variable's assignment in its entirety. So some of these satisfied clauses from before may now become unsatisfied when we change a variable. So, in this example right here, if flipping variable x changes 100 clauses from unsat to sat, but at the same time changes 200 clauses from sat to unsat, we're making progress in the wrong direction. Right? We're losing the amount of satisfied clauses. So we'll fix that by maximizing the net change in satisfied clauses. So I think we'll talk about this slide right here. The basic idea is see how many unsatisfied clauses become satisfied, see how many satisfied clauses become unsatisfied, take the difference and maximize that. So let's take a look at these vocab words. Make count is going to be the number of clauses that become satisfied if we flip a variable. So out of this quantity of unsatisfied, how many of those become satisfied? In this case, it would be the make count would be 20. Because I'm saying we went from 80 unsatisfied to 60 unsatisfied from that grouping right there. So 20 of them have now become satisfied. But at the same time, maybe some of these satisfied clauses became unsatisfied. So maybe of these 20, 10 of them are become unsatisfied. So in that case, the break count would equal 10. So however many good become bad is your break count, and however many bad become good is your make count. If we take the difference of make count and break count, that tells us the net change in satisfied clauses. If we maximize that, then we're making the biggest amount of progress. Let's see it through an example. Should make a little bit more sense. So this is our SAT formula. And we're starting with just any assignment, any solution. So we'll choose a random assignment, which just so happens to be setting all of them equal to false. So we're at some solution vertex right here. And we're going to crawl through our graph. The way we do this is compute the make count, the break count, their difference, and then figure out what's the maximum of that, and then flip that variable. So let's see it in action right here. Let's take a look at this first column right here. Variable 1 is currently false. To determine make count, we will say, if we change this value of false for variable 1 to be true, how many unsatisfied clauses become satisfied? In this case, it's just 1. This last clause here will now become satisfied. This third clause is already satisfied, so it doesn't contribute to the make count. The break count says, if I change variable 1 to false, if I flip it, how many clauses become unsatisfied? In this case, clause 3 doesn't become unsatisfied because this variable still satisfies it. And that's the only one that could become unsatisfied. So nothing becomes unsatisfied. Break count is 0. Let's just quickly look at variable 3 because this has it for both. If we flip variable 3 from false to true, this second clause becomes satisfied, and the fourth clause becomes satisfied. So it has make count of 2. The third clause becomes unsatisfied. So it has a break count of 1. You compute that for all of your variables, find the difference between them, and the variable we choose to flip is the one that maximizes that difference. Because this is saying, like, okay, 2 is the maximum. So this says, if we flip false, this x2 equals false to true, then 2 more clauses are going to become satisfied. So we choose that one. We flip 2 to now being true. And sure enough, we now have 3 clauses satisfied instead of 1. So, we would keep doing this until we satisfy everything. So again, compute the make count and break count. What's the make count and break count for variable 1? Or just choose any variable and give me its make count and break count. It's one person. I'll move past it.
One is 0 and 0.
1 is 0, 0. Thomas, do you want to give another one? 2 is what?
Break is 2.
Make.
Make is 0.
Nice. Michael, 3.
Make 1. Break 1.
Yeah, that seems right. So 0, 0, 0, 2, 1, 1. Let's hope that's correct. Yes, it is. Again, compute the difference. Choose the maximum. In this case, there's a tie, so we'll just break it arbitrarily. Choose that variable. And then we flip it, because that's the operation. So 3 becomes true. Do the same thing. Compute the make count and the break count and the difference. And I won't bore you with it because you already know how to do it. So that's the chart once again. It tells us to flip variable 1. We do that. Everything is satisfied. So the idea of what are we improving when we move from vertex to vertex? It's really the amount of satisfied clauses. Eventually we want all clauses to be satisfied. Here, maybe not all of them are satisfied. But if we always step in a direction that increases the number of satisfied clauses, hopefully we'll reach here. This is what we call greedy SAT, because it's greedy.
Does this always work?
No. Similar idea to before. You can get stuck in like some local maxima, local minima. In fact, yeah, there you go. It's not guaranteed you find the optimal or feasible solution. It's just you might start at a bad place and you might get stuck in some local optima. So again, still just a heuristic. Actually, this is an example right now of like how you would get stuck. So different formula. We start with false, false, false. The make count and break count, I gave it to you already. So once you do all the operations, it says let's flip variable 1. So you do that. It's now true. Again, compute the make count and break count. I did it for you again. Which one will we change now? 1. And if we do that, we're just flipping 1 back and forth. So we would never really escape that. Good question. Okay. Who took CIS1921 in the springtime? Not everybody? Okay, that's okay. So the next little bit might be familiar to some folks who've seen this or some variation of it. Others maybe not. We're still going to talk about it because it's kind of interesting. But before we get there, let's just talk about this. So there are ideas of like if we are in a local optima, some ways we can escape it is just to restart entirely. You know, whenever we feel like we haven't improved any further, it's a local optima, just start with a new random assignment and go from there.
How do you know if your local optima is not the global one?
Yeah, that's a really good question. Sometimes it's clear, like with SAT, you can just try it out and see if it satisfies it. If not, then you're probably in a bad spot. With TSP, you may need to have like some sort of additional information associated with the problem. Sometimes that's given to you, so yeah. So, you know, here's some problems. One problem is that this greedy heuristic is a little bit slow. We have to compute the make count and break count for all of our variables within our formula, which can take some time. So let's try to build something a little bit better. So we'll consider something called walk-sat. And for now, we'll just consider 2-sat. So, you know, formula where each clause has 2 variables within it. Actually, I kind of like the diagram. So phi looks something like x1 or not x2, and x2 or x3, and x1 or not x4. Each one of these has 2 things within it. And so our algorithm is as follows. Start with any assignment of phi, so just like before, start at some assignment. And then we'll just choose a clause from C that is not yet satisfied. And to fix it, we'll just choose one of the literals in C and flip its variable. So, you know, if I have an assignment to this, maybe it's x1 equals false, x2 equals true, x3 equals true, x4 equals false. Under this assignment, this first clause is not satisfied. False or false is false. So walk-sat is saying, find some sort of clause that looks like that. Choose one of the variables within it, either x1 or x2, and just flip its value. So maybe we say, x1, let's make you true, because that would satisfy the clause. And then keep on doing that. You know, keep choosing clauses that are unsatisfied and flip the variables. Makes sense, right? We're just kind of improving it directly. There's no guarantee you'll finish, but whatever. So, you know, here's an example. It's a better example. Start with some formula right here, some assignment right here. Choose a formula or choose a clause that's unsatisfied. Randomly select one of the variables within it. In this case, it chose 3. And let's just flip that. So now our first clause has become satisfied. Hooray. But of course, other clauses might become unsatisfied. And if that's the case, then we arbitrarily choose an unsatisfied clause, in this case the second one, and choose a variable within it to flip. In this case, 1. Again, it fixes that clause, but maybe other things are bad. Again, choose something else. Maybe we randomly choose 3, which is not great because we were already there before. So we change that, and again we're back at the first clause, and so on and so forth. And here we're there, keep on doing this. Okay, we got to a solution. Idea of walk-set makes sense? Yeah, pretty clear. Cool. So,
Isn't this very similar to like what we do in our head when we're like trying to solve like a SAT problem?
it's kind of similar to that, yeah. You sort of like greedily find a
Yeah.
clause and fix it. Very similar to that, yeah. So, okay. Let's focus on this last point here, the state of walk-set. It's just another vocabulary term. This is going to be a number that says how many variables in the current assignment agree with the true assignment. So I don't really like the variables that are used up there. So we have our formula of phi. And let's say the true assignment, the satisfying assignment is called S star. And our current assignment, at some time, we'll call it S sub t. The state of S sub t, which is where we're at in our walk-set, is how many variable assignments match with S star. So if S star says x1 should be true, and we have x1 equal to true here, this will contribute 1 to our state. Maybe this is the entire comparison. We would say that the state of ST is 1. 1 variable matches. And there should be an example. There will be an example in just a moment. We're going to kind of view this as traversing a... whatever. It's called a Markov chain. We're going to be at these different states. So these vertices represent states. So here, 2 vertices match with the true assignment. And as we do an operation, our state will change. So this graph is saying that either it'll change to state 3 variables will match, or it'll go to 1. And we'll flesh this out in just a moment right here. But keep this visual in the back of your mind. So here is a proper explanation of it. So the current assignment, so this means like as we're conducting walk-set, as we've chosen a variable and flipped it, and we have this like current assignment right here, we'll call that S sub t. And the true assignment that satisfies our formula, we'll call that S star. S star has state 5 because it has 5 variables, it is the true solution. In this example, ST has state 3 because 3 variables match on both sides. Just x1 and x4 have different assignments. So as we perform an operation of choosing a variable and flipping it, its state is going to change. Right? If I choose x1 and flip it, the state is going to become 4 because, well, another one matches now. So we're going to see how it changes. So we'll consider a couple of cases. Case 1 is when we choose an unsatisfied clause, both variables in that clause happen to differ from S star. So remember, we choose unsatisfied clauses, and we're in the world of 2SAT. So there's only 2 variables within that clause. So case 1 is saying our current assignment, both of those variables happen to differ from the true assignment. Then, no matter what variable we choose to flip, if we randomly choose x1 to flip, then we have made progress. We would be in state 4. But also, if we chose x4 to flip, we would also make progress and move to state 4. So in this case, no matter which variable we choose to flip, we're increasing our state. We're getting closer to the true assignment because it's telling how many variables match. The other case is we choose an unsatisfied clause. So the colors might not make sense here, but both of these evaluate to false. However, now only one of those differs from the true assignment in the satisfying assignment. So yeah, in this case, like x2 matches, but x4 does not match. And again, we randomly choose one of them to flip. If we happen to choose x2, then this will flip to true. Our state will become 2, because we've lost one match. But if we instead choose x4 to flip to true, then we have made a new match. Our state increases to 4. So these are the only two cases you need to consider. The other case, which would be like if both variables matched in S star, we don't have to consider because S star would satisfy the clause, and we're looking at an unsatisfied clause. I'll pause here if there's any questions, and then we'll make the realization. So case 1 said, if we fall in that case, no matter what we do, we make progress to state 4. And in this case, half the time we'll make progress to state 4, the other half of the time we won't make progress. We'll move to state 2. And so the eventual conclusion you can come to is that the probability that your state at the next time step after you perform a flip operation is one more than the state that you currently started at is at least 1/2. Because in one case, you're always guaranteed to move forward to that state. In the other case, half the time you move to that state. So we're bounding it by 1/2. And the probability of going backwards, so the probability your state decreases by 1, given that you started at I, is at most 1/2. It's just that one bad case in case 2 that we just happened to choose the wrong variable. So when we think about the Markov chain from before, what we would see in the visual is that state 1, we can either go to state 2, or we can go to state 0. Same thing with state 2. We can either go to state 3 or state 1. But more importantly, these have some sort of transition probabilities associated with it. The probability we go from 1 to 2 is at least 1/2. And the probability we go backwards is at most 1/2. And that would be the same for all of these edges, except for some edge cases right here. Yeah, whatever. Well, no, not that one. Is that relatively clear? Traversing states, they have some sort of associated probability of making progress. Right. We're going to start somewhere, some solution that has some state, and we want to eventually, hopefully, crawl to n here by this random operation. It turns out, when you do the math, in expectation, you'll reach state n, meaning all variables are satisfied, in O of n squared steps. Just following this random procedure. Perhaps interesting. I don't know, I found it kind of interesting. Who cares? Like,
Oh, is this supposed to be a lecture?
yeah, I think.
Oh, sorry, I'm in the wrong class.
That's all right. Stole away from the climax of this lecture. Who cares? 2set's not NP complete. Like, why did I waste your time with all of this? 2set is a known polynomial time solution. You convert it into strongly connected components, and you solve that, and then be happy with life. Right? What happens when we try to do this for 3set? The structure stays the same. We have the concept of states, because this is just how many variables match our true assignment. So this Markov chain, the structure of it looks exactly the same. The thing that changes is the transition probabilities. It so happens that the probability of making progress is now at least 1/3 instead of at least 1/2. And the probability we move backwards is as bad as 2/3. And let me read my notes for this exactly because I wanted to give the correct intuition. Okay. So at time t in our algorithm, like at some point t, we choose a clause c and flip one of its variables. That clause is not satisfied under st, but it is satisfied under s star, which means the variables within that clause, maybe we're looking at the clause x1 or x2 or x4, the variables within this clause, if we look at those variables in st, not all of them can have the same assignment as s star. Right? If I had if this occurred, that my partial or my current TOR matched on all three assignments with S star, I'm saying this cannot happen because this is an unsatisfied clause. We're always looking at unsatisfied clauses. But S star guarantees to satisfy this clause because it satisfies the entire formula. So this cannot happen, which means at least one of the three variables in C differs. At least one out of the three. Which means the probability that we select the correct variable to flip is at least 1/3, because at least one out of those three differ. So the structure of the chain looks the same. It's just these now change to something like this. Right? It's just the transition probabilities are different. This is bad because now we have a larger force pulling us backwards. We're trying to go to the right, but we have this 2/3 force pulling us in the backwards direction. That blows up the runtime to 2 to the n. Not good for 3-sat. So, we can't just immediately use this idea of selecting things and flipping it for 3-sat. It's not going to work immediately. However, there's some improvements you can make. One idea is to use this idea of restarts, that after 3n steps, if you don't find the satisfying assignment, restart. And a good question is why 3n? The simple answer is it's just arbitrarily chosen. The more complex answer is that there's an associated probability that you won't find a solution after 3n steps, and that probability is very, very small. So we say, since it's so small, let's just use 3n as the criteria. Whatever. So if you just use this idea of restarting, the runtime somehow gets to this, 4/3 to the n, which is still exponential, but it's not 2 to the n. Questions on walksat? It's a little bit more on walksat in practice. One idea is to combine the randomness of walksat with greediness. Both have their pros, both have their cons. What happens if we combine them? So this random greedy walksat algorithm says it's the same idea. Choose a clause that's not satisfied. And now with probability P, we'll do the flipping thing, where we just flip one of its variables. Same thing we did in walksat. And with probability 1 minus P, we'll do the other idea, the greedy idea, of figuring out which one maximizes the number of clauses that become satisfied. It's a mixture of the two ideas that we saw together. Now, this tends to work out pretty decently. The question is what do we choose for P? And so this dude from UCSD says the following, that If the ratio is around 4.25, p equals 0.5 works well. Otherwise, if p is less than 0.5 often works better. I don't know the logic behind this. I trust him enough to just believe it. But as with a lot of things we've seen in this class, often it's just helpful to have experimentation. Do your own experimentation, gather trends on what works better, and then just roll with that. Questions on that? Okay, so that's all the content. Just as brief reminders, submit your proposal by Saturday. No class next week. Last class will be the following week. You'll do your project presentations there and fill out the form on Ed. That'll help me plan for the last lecture of what I should talk about. Otherwise, yeah, that's pretty much it. Are free to go.